Hi, everyone, and welcome to online lecture 31, our final exam review and our last online lecture. So I'm going to jump right in here with the slideshow and tell you that we're going to have 6 questions this time. And these are examples of the sort of questions that could be asked on the final. At least one of these 6 questions will appear on the final. Answer choices may be in a different order, but the question will appear as is. Okay. Suppose that a researcher wants to know whether a student lives in a dorm, apartment, or off-campus housing is related to the number of times a student will arrive late to their class. What is the dependent variable and what is the level of measurement for this variable? Okay, so first of all, we got to figure out the dependent variable, right? So we have 2 variables here. We have where the student lives and number of times a student will arrive late to their first class. Okay, so I was just pausing to give you a little opportunity to figure it out. But anyhow, I'll jump in right now. So pause if you're still thinking. So the answer is the dependent variable is arriving late to their first class, and ratio, because a student could arrive 0 times late to their first class, and that would mean they never arrived late to their first class. So it's the number of times a student arrives late to class, and ratio C. Okay, let's move on. You are told that for a given study that alpha equals 0.01 and that power equals 0.75. Which of the following statements is true? Okay, so pause, think about it. Okay, all right, so here we go. The alpha and the type 1 error are the same thing. Alpha and type 1 error are the same thing. Okay, that doesn't eliminate much. It just eliminates choice A, and now we're down to choices B, C, and D. Now, power plus type 2 error is 1. Power plus type 2 error is 1. So 1 minus power is type 2 error, or 1 minus 0.75 or 0.25 is type 2 error. So the answer is D. The type 1 error is 0.01 and the type 2 error is 0.25. Okay. Next one. A researcher administered a scale measuring concern for farm workers. High scores mean high concern to 10 male students and 10 female students after they attended a film about union organization of farm workers. Now, this researcher believes that concerns for male students will be higher than concern scores for female students. Assume alpha is 0.05, and what is the appropriate tabled cutoff score for this test? Okay, so as an aside, I'm going to first ask you, which test would you use? Okay, and we have 4 choices up here: the z-test, the t-test, Pearson correlation coefficient, or one-way ANOVA. So is it a z-test, one of the t-tests, correlation, or one-way ANOVA? Think about that. And I will tell you now that it is a t-test. It is a t-test. Now, I'm not going to tell you which t-test it is yet. I want you to think about that. All right. So now, think about which t-test it is, so we can actually get into the table and look it up. Have you thought about it? It's the t-test for independent samples. So why is that? It's because we have male students and female students, 2 separate independent samples that we are comparing. Okay, we're comparing their concern scores. Okay, so now we can move on to the next one. And now that we know that it is a independent samples t-test, we can actually start to think about how we're going to get the table cutoff score. So I'm going to go to a new share. I'm going to go to the t-table. So you can look at that. And first we have to remember, was it one-tailed or two-tailed? And if you recall, they said male scores would be higher than female scores. So one-tailed. We have to know what the alpha was. Well, they said it was 0.05. So we're over here in the one-tailed land, we're down 0.05. Okay, so the last thing we have to know is the DF. Okay, so let's go back again. I'm going to go back one more time so we can see how many students there were. 10 male, 10 female, minus 2. It's 10 plus 10 minus 2. So 20 minus 2 is 18. So 18 is our DF. This, by the way, is why it was really important that you knew which t-test it was. Because for the other two t-tests, the DF is simply n minus 1. You would have come up with something different. Okay, so one-tailed 0.05, we're looking for 18. It's right here. The answer is 1.734. That's 1.734. So let's go back. And the answer is C, 1.734. Okay. Also, one other thing I just want to point out real quick is, remember, it was asking for a tabled cutoff score, and that was highlighted, it was bolded, I should say, and underlined. So this wasn't figuring out the actual t-score for this data, which we weren't actually really given any data, just given the information about it. It was the table. Okay, just wanted to point that out. All right, now we can move on. So Marge completes a research study looking at the relationship of artistic ability to sensitivity. After she collects her data, she calculates the Pearson correlation coefficient and finds that R equals negative 0.40. What proportion of variance in sensitivity is accounted for by artistic ability? Okay, so how do we get this? How do we get from Pearson correlation coefficient to proportion of variance? So again, pause, think about it. And now I will tell you that you square it. Negative 0.4 times negative 0.4 is always negative times negative. Remember, always gives us a positive. So we already know it's B or D. Negative 0.4 times negative 0.4 is actually 0.16. So the answer is B, 0.16. That's B as in boy or baby or whatever you like, 0.16. Okay. Which of the following tests can never be used to determine causality? Which of the following tests can never be used to determine causality? So pause, think about it. And I will tell you that the answer is Pearson correlation coefficient. That's the only test we talked about where we can never use it to determine causality. Why? There's no independent variable and no dependent variable, okay? And if we don't have an independent or dependent variable, that's it, game over. We can't ever get to causality because we wouldn't know which caused the other. So when you're thinking never being able to determine causality, you should think Pearson correlation coefficient. Okay. All right, next one. Dr. Crabapple plans a study in which a crucial step is offering participants a food reward. The researcher has chosen 3 foods: apples, cookies, and candy. The null hypothesis states that 25% of participants will prefer apples, 50% of participants will prefer cookies, and 25% of participants will prefer candy. To test her hypothesis, she obtained 60 participants and asked their food preference. She finds that 18 preferred apples, 28 preferred cookies, and 14 favored candy. What is the expected frequency for the number of persons that would prefer cookies? Okay, so that was kind of a long one, so pause, think about it. Okay. So let's break this down. Okay. What do we know about the expected frequency? It matches up with the null hypothesis. So really, this stuff down here about 18 preferring apples, 28 preferring cookies, and 14 favored candy, that's irrelevant. You could cross that sentence off, and you would still be able to solve this problem. Okay, so what we do to get an expected frequency is we take the total, which was 60. We did need to know that it was 60 participants, times the expected frequency, or the null, for that cell. So we're looking for cookies. So what percent preferred cookies? 50%. So it's 50% of 60, or 0.5 times 60, or D30. D30. Okay, we're just taking 50% of 60. Had we been talking about expected frequency for the apples, let's just do that for fun. It would be 25%, or a quarter of 60, or 0.25 times 60. In other words, 15. It would have been 15 for the apples. Okay, but in this case, it was cookies, so 30. Okay. So those are the questions. I quickly put together, or I want to quickly review what I put together, which is some symbols for you guys, just so that you have all the symbols in kind of one sort of place. So if you see a mu or mu d, it's the population mean. X bar or D bar is a sample mean. Sigma squared is a population variance. Sigma is a population standard deviation. S squared, or S squared D, or S1 squared, or S2 squared, or S squared pooled are sample variances. S, or SD, or S1, or S2, or S pooled are sample standard deviations. Now I want to make a point about this next one. Now what I have here is true. Sigma X bar, or S of X bar, or S of D bar, or S of X bar 1 minus X bar 2 are all standard errors of the mean. However, there is an important distinction to be made here. This first one, the sigma X bar, that's a population standard error of the mean. All the others are sample standard errors of the mean, or standard error, or sample standard error of the difference mean, or sample or standard error, sample standard error of the difference between means. But these are all samples. The S is sample, the sigma is population. So that's an important distinction to be made. All right, let's move on. Okay, N is sample size, SS is sum of squares, DF is degrees of freedom. This symbol right here means alpha. P is probability. Z is a Z-score or Z-test. T is a T-score or T-test. And this symbol here, summation, add it all up. Add up everything that comes after that. Okay, let's move on. SSB, sums of squares between. SSW, sums of squares within. SST, sums of squares total. DFB, degrees of freedom between. DFW, degrees of freedom within. DFT, degrees of freedom total. What do these all go with, by the way? This next batch, can you remember? Goes with ANOVA. Goes with ANOVA. Okay, MSB, mean of squares between. MSW, mean of squares within. And F test or ANOVA. Okay. R, Pearson correlation coefficient, R squared, coefficient of determination or percent of variance accounted for. That hat's a little off center. The hat should be right over the Y. Y hat is predicted Y value on the regression line. A is the intercept, B is the slope. F of O or O is the observed frequency, F of E or E is the expected frequency, and this funny X squared is our chi-square statistic. Okay, so if you want to make notes of this, of course, you can pause at each appropriate point and take notes or what have you. Okay, so that's it, guys. It has been a crazy semester, but I hope a decently good semester. I hope it's been good. It has definitely been a significant experience, and I wish you all the best of luck on the final. Okay, take care, be well, and good luck.